Hi. We were in chapter 1. What we have done already, we examined the digital signals and systems, and inside the digital systems, that blue area, which is the processing part of the digital system, what is inside of that processing, we examined the elements that we use in this processing unit. These elements, they were these gates. We have examined those. Now what we are going to do, we said this systems, digital systems, accepts only the symbols 0 and 1, no other symbols. But in our daily life, we've got different symbols. So we've got to do the coding business. That is the coding business. We are going to daily life symbols to 0, 1 symbols in order to be able to make an input to that digital system. We need to do coding. So we will be examining this coding here, numbers and letters in binary, and then in daily life we are doing the arithmetic operations, that is multiplication, summation, division, and subtraction operations, all these operations in decimal. But in here we can't do it in decimal, we've got to do it in binary. That means we're going to use base 2. So how we are going to use the base 2 arithmetic operation is these two slides that we are going to examine. So let's move from this one and come to this. Change the, okay. Clear the previous one. So it says positional number system. Why it is positional? Because each position has a coefficient. So the position is important. That's why it is called positional number system. Any decimal number can be represented in this form. What is this form? You've got this R, which is radix. Radix is the base. So radix is 10 if we are in decimal number system. So R is equal to 10. That D is a set. This set includes these 10 symbols. These symbols, the symbols that we know in arithmetic. So in decimal system, we've got 10 symbols. 10 is not included here because it starts from 0. So total symbols is this. By using these symbols, we can represent any number. So how we are representing any number? With a formula. Let's say if you want to represent 541, so this position is the position of 10 to the power 2. So the position coefficient, that is, you might call it, 4 times 10 to the power 1, and the last one is 10 to the power 0. So when you add them up, it's going to 500 plus 40 plus 1, add them up, 541. So that is the representation. So what is done actually, that is counting businesses, that you, in order to reach to 541 by counting, you're going to go step by step, you end up with this. So that is what is given to you with this formula is the same. So this formula is true for all bases. That means in any base, that means in any radix, with the symbols in that radix, you can write a decimal number. So you can transfer this radix number to decimal number. In other words, we could say it like that. So you see here, for example, randomly I have chosen that. So what is this number in decimal with that positional formula? So our radix is 2 and our symbols is 0 and 1, nothing else we've got. So this is that number here includes 0 and 1 only. So base 2 number. So this position has got 2 to the power 3 times 1. This is this one. And the second position is 2 to the 2 and that's 0. So that's 0 I am talking about. Plus 2 to the power 1, that one here multiplied with this one, plus 0 times 2 to the power 0. So let me show it. These are the coefficients of the positions. That's why the positions are important. This position, when it is on the right hand side, the lowest position, 2 to the power 1, this is the radix over first position, second position. Third position is this, fourth position is this. Fourth position coefficient is this. So that is 8, that is 4, that is 2, that is 1. 2 to the power 0 is 1, isn't it? So then 8 times 1, 8. So 4 times 0, that gone. 2 times 1 is 2. And 2 to the power 1 is 1, multiplied 0, that is gone. So the 0 ones has gone. What is left? 8 plus 2 gives you 10. So that number here, 1010, 2 base, is equal 10 in decimal. So I use that formula, transfer 2 base number to a 10 base number. So this is true for all bases. So for base 8, so if you look at here, you've got only the symbols between 0 and 7. There is no 8 here. In this decimal system, you don't see any symbol apart from 9, isn't it? 10, how are you going to write the 10? Use the position. So the first position is not enough. First position is enough for you to use your symbols. And then you're going to increase your position. So make a tens position, decimals position, 10 to the power 1. So you are increasing that value here. So you might consider this second position 0 here. So when this first position is full with your symbols, so you're going to increase the second position, which is this one more, from 0 to 1. So you're making counting. So you can represent any number in decimal by using these decimal symbols. So similar thing you can say for base 2 and base 8 as well. And when you come to base 16, so you got 10 symbols as the same as is base 10. So we need 16 symbols. For these 16 symbols we use A, B, C, D, E, F. So the total number of symbols in this base 16 is 16. So let's come to the second slide here. So we said by using this formula we can transfer any base number to decimal number. But how we are going to do the opposite of it? Because in order to transfer our decimal symbols to binary, we need the opposite coding. So how we are going to do it? So consider that 558. This is a decimal number. This decimal number, how we are going to write this decimal in binary? So in maybe schools, in Lisa times, I don't know where, you have seen that to find it, you're going to write that 558 divided by 2, find the division here, continue this until you end up with a remainder 0. When the remainder is 0, write all the remainders that you have from right hand up to the first one. So if you write all these reminders, writing from the left hand side to the right hand side, you're going to end up with base 2 number representing this 258 base 10 number. So this is a long process, and this process is not easy to do by hand, but not easy to do in computer as well. You've got to do the division operation. That division operation, not an easy job to do. But we have an alternative to that, which is faster than this. Is this? We know each position has got a coefficient. So the coefficient is written here: 2 to the power 0, 1, 2 to the power 2, up to 2 to the power 8. So the decimal corresponding numbers to those positions is 1, 2, 2 to the power 2 is 4, 2 to the power 3, 8, 2 to the power 6 is 64, 2 to the power 8 is 256, sorry. So how I am going to write this decimal number in binary? That's the question. So once you write these positional coefficients here, it is easy. The nearest number to that decimal number is 256. So you're going to put 1 in this position. What is left is 2. So in the 2 position, if you put 1 as well, so altogether the other positions are going to be 0, because addition 1 time this position is 256. 0 positions are going to give you 0. This position 1 times 2 to the power 1 gives you 2. So add them up, you're going to add 158. That's that one. So what is the corresponding base 2 number to this decimal number? Is this. Base 2 corresponding to this. This one easy to write. So you could do it by hand. Do it by doing this division. You get this. And how you can make it faster, this one or this one, so you can compare it to your own. So we have, as I said here, this one seems easy, but we are using our eye and our mind. So this process is not available in the computer. So in computer, you've got to do that arithmetic operation to end up with these reminders, which is difficult. So what they have done, is there any alternative to write a binary number corresponding to a decimal number? So they introduced this new one method. This new one method is called binary coded decimal. This BCD coding comes with the first letter of binary, first letter of coded, and the first letter of decimal. Write them together, BCD coding. So what is this coding? This coding is this. In decimal number, any decimal number has got digits on it. These digits is going to be represented in binary with 4 bits. So if you represent each digit separately as 4 bits, you end up with BCD coding. So we can easily do this. So we know the positions of the 4-bit binary numbers: 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So that is 1, 2, 4, 8. So if your decimal number, the first digit is 8, you're going to write this underneath that 8. So the second digit is 5. 5 is 4 plus 1, isn't it? So the other 0. That's 5. So I transfer that decimal number to that number, 0, 1, 0, 1. But I consider each digit separately. The last one is 2. 2 is this position 1, the other positions are 0. That's 2. So that's 2. So if you write those near to other one, so you're going to end up with binary symbols. So this now, what we have found here is binary coded decimal of this decimal number. So this is different from this one. So the opposite operation is also easy. If something, a binary symbol is given to you, if they said that this is a binary coded decimal coding, from that you can find the decimal number easily. How you're going to find that? So this is represent of 8. So from a table, you could easily find it. This is 8, write 8. This is, so you're going to make groups of 4. So if this is given to you, you're making this group of 4s. So this 4. You're going to start from the right hand side to make the groups. So each group is going to be transferred. This is, each group has got 4 bits. This 4 bit is going to be transferred to decimal number. So you can easily find this decimal number. So the process of coding decimal number to binary, binary coded decimal number to decimal is easy. It wasn't easy here. But that's a benefit. But what is the disadvantage? Disadvantage is this. The number of bits that you see here, let's count it, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 bits you got in this coding. In this coding, you've got 12 bits. Although the conversion is simpler here, but the number of bits required to represent the decimal number is higher than this one. So this is what we've got to pay for that. The meaning, when it is advantage, when it is disadvantage. So if the conversion is critical for you, you've got to use this conversion. But if you say that only the speed is important, so that is easy, because the number of bits is less, means you could get the results faster when you compare this one. So 30% faster this one is to this one, isn't it? But in practice, in the digital systems, this binary coded decimal coding is quite commonly used. Let's come to the last one, clear the previous ones here. So in the previous ones, we examined the decimal numbers. But in our daily life, the symbols that we are facing with are not only the decimal numbers. There are some other symbols. These are letters, aren't they? And there are some other symbols that we use in our daily life. These are the quotation marks. So you can consider all these symbols that we use in our daily life is this group. You might call it keyboard symbols. So in your computers, in your keyboards, you're going to see all these symbols. So we've got to be able to represent these symbols as 0 and 1s. If we've got to transfer this to all these daily life symbols to 0s, 1s, because the digital system that we use accepts only these symbols, not the other symbols. These symbols, if you send them this symbol, it doesn't accept that. Therefore, we've got to transfer these symbols as well, not the numbers only, but these all symbols to 0s and 1s. So there are some standards for it. This is just one standard. It is called American Standard Code for Information Interchange, ASCII. Is this one? It is a commonly used one. So how are you going to write any symbol in binary by using this table is easy. Assume that you're going to write the symbol small a. So you're going to write this column code first, that is 110. That is the column binary numbers, and the corresponding row code is this. Write it next to it, 0, 0, 0, 1. So that is the representation of small a by using this coding system. It is this one. Okay. So now we are in a position now we can transfer all our daily life symbols to 0, 1 binary symbols in order to be able to apply these symbols to our digital systems. So in order to transfer all these symbols to that digital system as an input, I need how many bits? 7 bits. So if you've got these 7 bits, 1, 2, 3, 4, 5, 6, 7 input here, then when you click that A, that means in your keyboard, when you click that A, underneath to your digital system, you are sending these 4 bits, these 7 bits, 1, 1, 0, 0, 0, 0, 1. Okay, so this operation is done underneath your keyboard, on your key. Any key you touch, on the other side, you are sending these symbols to your digital system. So that is the end of this slide, this video. Let's stop here.